Spectroscopy is the measurement of chemical concentrations based on the interaction of light with the system. In our case, we're going to use visible light to measure the concentrations of species like phosphate, nitrate, iron, and in the lab this week, metal concentrations in the presence or absence of EDTA. Color plate 6 from your text shows how solutions with added aerochrome black tea, a dye that complexes with metals, how the color changes in the presence or absence of EDTA. Light is a wave, just like waves coming into the beach on the edge of the ocean are waves. These waves have wavelength, which is the distance from peak to peak of the oscillating wave, and they have frequency, which is the number of oscillations that occur within a unit of time, typically within a unit of 1 second. The energy of light is related to its frequency, or nu. Frequency and wavelength are related through the speed of light, so we can also write energy as equal to h nu, or hc over lambda, where h is Planck's constant, 6.626 times 10 to the minus 34 joules seconds, and c is the speed of light, 2.997 times 10 to the 8 meters per second. I will underline those key terms. In visible spectroscopy, we use wavelength as an index of energy. And because energy is proportional to 1 over wavelength, short wavelengths have high energy and long wavelengths have long energy. In infrared spectroscopy, we often want to display the spectrum proportional to energy, and so the units used in IR are wave number, mu with a hat, and that is directly proportional to energy. I'll highlight that term. So if we know the frequency of light, or we know the wavelength of light, we can interconvert between frequency and wavelength, and we can also compute the energy. The energy of light is important because it is the absorption of quantized units of energy that result in absorbance. This diagram shows a number of different spectroscopic transitions: absorbance, fluorescence, phosphorescence. We're interested in the middle part of the diagram, where absorbance of light goes from a ground state, represented as the black bar at the bottom of the diagram, to an excited electronic state, S1. And S1 has many levels because of vibrational and rotational energy differences in the molecule. And so we absorb from the ground state to a range of excited states. The energy that's absorbed is lost to the solution through molecular collisions. So in standard absorbance, the mechanism of transition is photons in, heat out. If you shine a light on a colored solution, it gets hot. Notice that S1 only has specific energies, and so only specific wavelengths can be absorbed. This is what gives our solutions distinct color, and this is why we have to pick specific wavelengths to make absorbance measurements. This diagram shows wavelength or frequency along the x-axis and the type of transition associated with different energies. So you'll notice that X-rays involve the ejection of electron and the breakage of chemical bonds. Infrared energy is low energy, and it causes molecules to vibrate or rotate. And we're interested in ultraviolet and visible light, which has enough energy to cause electronic transitions, but typically not enough energy to break atom-atom bonds. This is a simple table of the name of different regions of electromagnetic radiation and the energy and wavelength associated with the midpoint of each region. Again, we're interested in visible light 900 to 400 nanometers. It is important to remember that the color of the solution that we observe is the opposite of the color that is absorbed. And so this table shows the wavelength of maximum absorption, the color of the absorbed light, and the color of the observed solution. If we want to study a red solution, we're going to use blue or blue-green light in our spectroscopic determination. So how does absorption work? It's important to recognize that absorption is a first-order process. So the absorption of light is first order as the light passes through a colored block of solution. So let's begin by looking to the left-hand side of the diagram. Starting with an incident flux of photons P0, let's say 100 units, those photons are going to be absorbed over a small interval dx. The change in photon flux dp is going to be equal to negative p, or negative of the incident flux, beta, which is the molar absorptivity of the solution, c, which is the concentration of the solution, and dx, which is the small interval over which the light is being absorbed. We can reorganize this equation into a standard first-order relationship. So dp over p is equal to negative beta concentration times dx. As a practical matter, we don't measure the absorption of light over a small interval. We measure the absorption of light over a defined path length, x. So we're going to integrate the first-order relationship. So the result of that integration is that the negative log of p over p0 equals beta times concentration times the path length x, where beta is the molar absorptivity, or the efficiency of promoting an electron from a ground state to an excited state. C is concentration, that's typically what we want, and x is the path length of the analytical cell. As a practical matter, it is common to define T, the transmittance, as P over P0. P0 is the flux of light going into a cuvette, and P is the flux of light coming out. The same ratio on a logarithmic scale is the absorbance, and we can write it as the negative log of P over P0 equals absorbance, or in this case, a positive log of P0 over P equals absorbance. They are the same thing. Our integration used the natural logarithm, so it is common to multiply beta by the natural log of 10 to define what's called the molar absorptivity, which can now be related directly to absorbance. So now we have the basic relationship that you all learned in introductory chemistry. Absorbance is equal to epsilon, the molar absorptivity, B, the analytical path length, and C, the concentration. We make absorbance measurements using a spectrometer, and a spectrometer consists of a light source, a wavelength selector, which separates the light source into a narrow range of wavelengths. In our case, we combine these two together by using a light-emitting diode. That light P0 is now passed through a sample cell of path length B, and finally the light hits a detector where it's measured. We can always determine P0 by simply removing the sample cell. So if the sample cell is missing, the detector measures P0. Or we fill the sample cell with water, and we call that the blank, in which case the light detector measures P0. We then place the sample into the cuvette, and we measure the reduced light level P. We take the log of P0 over P to get the absorbance, and we relate that to the Beer's law relationship, A equals epsilon, B path length, C concentration. So to repeat these concepts, our spectrometers are very simple. The light source is an LED, which produces a narrow band of color. The detector is a photodiode that detects the flux of light coming through the cuvette. We don't need to measure an absolute flux because we always ratio P to P0. So we can actually use the voltage coming off the detector and ratio the voltage when we have a blank solution to measure P0 and an analytical solution to measure P. Absorbance is now related to EBC, and we also need a chromophore that produces an E that's greater than 0. So we're going to need to pick a wavelength where the chromophore absorbs light, and of course we can also play with the path length, which is what the phosphate group did and the iron group did in our analytical lake work. They changed the path length from 1 centimeter to 10 centimeters to increase the absorbance of dilute solutions. So as a practical matter, we make calibration curves. Calibration curves are plots of absorbance versus a known concentration for a series of known standards. The standards now can be plotted to determine a slope, and the slope is equal to the molar absorptivity times the path length. To determine unknown, we simply measure the absorbance of the unknown, extrapolate across to our curve, down to the concentration on the x-axis. So we solve for x in the expression y equals mx plus b, and again b should be pretty close to 0 in most of our simple spectroscopic applications, and m is equal to the molar absorptivity times the path length. Most of our analytical solutions add some sort of reagent to make the clear nitrate, phosphate, iron, cobalt, chromium, manganese, calcium, etc. solutions colored. These reagents work by forming complexes that have conjugated pi systems. Systems with conjugated pi systems tend to absorb visible light. So these are dyes, pH indicators, analytical reagents. As a final note, please don't confuse the B, the intercept in the Beer's law plot, with B, the path length of the solution. They have the same name, but they mean two different things. This concludes my first experiment narrating a lecture to be posted to the web. Hope you enjoyed it. See you in lab on Wednesday.